So I've been around the block a few times. I'm a startup guy now for more than 15 years, close to 20 years. Done all kinds of stuff. Wrote my first compiler when I was 15. Been doing distributed computing for 30, 35 years. First distributed computer was a Z80 mob doing some sort of data entry programming stuff. But I did all kinds of fun stuff along the way. And one of the most fun times of my life was doing the Azul, working for Azul Systems, building custom hardware for doing big business logic Java. And we did a lot of cool stuff in that hardware. It broke a lot of ground. It was new in a lot of ways. And some stuff worked fabulously well, and some stuff did not. So, hardware transactional memory. It's been around longer than maybe people think. Azul Systems did it in 2002. So, 18 years ago, something like that. And we're trying to make, at that time, we were trying to make random junk Java code run fast. And for that, the hardware transactional memory didn't work for reasons that are obvious in hindsight. But when we went into it, it seemed like it was an obvious thing to go do. It should just really, really work. So I say it doesn't work. Of course, the hardware does what the hardware does, and the hardware was functioning as expected. And the HTM would therefore allow you to transact through some number of cache lines doing multiple modifications and reading and writing and whatever. But there were conflicts every time that blew out the transaction, except in a couple of very narrow cases. And we'll get into that a little bit more. But things like you could focus the problem really tightly. So various kernel ops doing context switching and page table lookups, high-frequency traders doing games with direct-to-network byte buffer networking cards and the like, where they have very small amounts of code that they're handcrafting. They could get the HTM to work reliably. Otherwise, it didn't work very well. And along the way, the industry just found other solutions to running large parallel workloads. At the time that we started, large shared memory machines was the obvious way to do large, heavy workloads. And clusters and microservices were just getting started, and they weren't actually very viable yet. So this is a story about the hardware transactional memory effort that Azul did, closing on 20 years ago. It was not quite, but it's been a while. So the target audience for this hardware was big business Java. So web portals, web services, people who were serving up web pages by the millions a second if you're hitting heavy load on Black Thursday and everyone's buying everything, or Super Bowl tickets just went on sale or whatever, and your server gets slammed. So big parallel Java, big shared memory coding style, which at that time was perceived to be much easier than distributed coding, right? So these are thread pools and work lists. GC pauses would be an issue because you have very large heaps relative to what most people were doing, and a lot of locking around caches. So the theory was that we would put out a big effort for a big gain, and a big effort meant custom hardware. So big core counts, lots and lots of cores. Every task, every lambda, every runnable expression would get its own core. Every GC piece would have a core. You have multiple GC cores running, dozens. Cores for jitting, cores for hot spinning on I/O, cores for everything, and everything that has its own core. So lots of cores take lots of silicon, so the cores are simpler. They're not too simple. They're not GPUs, right? So they're actually running Java code. So classic 3HS RISC, 64-bit. They looked like a really common RISC instruction. They had smaller caches than x86s at that time, and a much lower clock frequency. Azul Systems didn't have the dollars that Intel does, and so we're always 2 process generations behind Intel, right? So you took the cheap process generation that was commonly available, and that meant you clocked a lot slower than Intel clocks. But we added some custom hardware, read barriers for helping the low-latency GC, a bunch of custom ops for doing like virtual calls and arrange bounds checks and stuff like that, and then hardware transactional memory. This is in 2002. Intel Haswell gets HTM like almost a decade later. And in fact, in 2014, they had some sort of bug and they had to go reboot their HTM and try again, but they got it right apparently. Okay, so what worked well? So we were supposed to be handling this irregular thread parallel workloads, and actually it worked fairly well. So people would have these web requests come in, they would do some lookups, some databases, some caching for the things, they would fire off 13 database requests, and they'd bunch of locking structures, and it would all come together and produce a web page and hand it back to you under an amazingly high load, so loads that no one else on the planet could survive at that time by 2 orders of magnitude. It was a huge difference. The GC was untouchable even today. At that time, so almost 15 years ago, we could handle 40 gigabytes a second of allocation on a terabyte of live data with the max pause in the low millisecond range. So it's max pause in the millisecond range. These days, Azul on x86 hardware will get it down to the low microsecond range. So it's a much better GC. And a bunch of other stuff's in there. I mentioned the custom hardware for doing vtables and range checks. Built-in JVM profiling that was still, to this day, you can't get. I could tell you what was in your L1 cache and what wasn't, and why you were missing in your L1 cache because this wasn't in it and that was, or whatever. You can't get that stuff today, even with sort of Intel hardware performance counters. So there's a lot of cool stuff in there. So the expected use case is that we're going to have all these parallel worker threads, and they're going to be doing these kind of unrelated tasks. And we expect there's a lot of shared infrastructure, and there's a lot of locking and synchronization around the shared infrastructure, so database caches of all kinds, web caches, and a lot of useless contention where people don't know how to debug it. They're still fighting data race bugs constantly, so they throw in a bunch of junk locks to try to make the program work at all. And the locks are very rarely contended because they weren't expecting to have any real contention there. So you get a lot of locking that causes reader-only threads to block on each other. And of course, they're blocking against the rear writer as well. And what we want is the hardware transactional memory to let us do parallel execution through locks, lock collision. The poster child here, did I get that right? Yeah. The poster child here was HashMap. There were lots of other kinds of codes being used for caching and for parallel shared structures that had locking. But HashMap was the most common case, and it's the one that was the most obvious that you could go speed up. You expect to see this large hash map that's shared across hundreds of running cores that are mostly reading and mostly hitting in the cache. The cache is very big. This is part of the efficiency to have a big shared memory machine. Occasionally somebody misses in cache. You have a writer comes in and occasionally wants to write something. So you want the readers to not block each other for sure. You'd like to have the readers not block with the writer if he's in different parts of the table. The table's very large. So, thousands and millions of entries. The writer is on a couple cache lines over here. 99 readers should be in other cache lines, not care at all, and just transact through. That was the goal. Parallel computation without lock-free computing, right? And without you rewriting your code base, right? Because you're going to take somebody else's junk Java code, whatever they wrote, and just run it in parallel better. Okay, so the goal was to elid Java locks, so let's talk a little bit about Java locks. And the reason to do elision is because there's a performance problem there, but there was well known that Java locks are hot, and there was a lot of work already done on Java locks to make them go fast. So sort of 3 performance domains. It wasn't contending, it was lightly contending, and it was heavy contending. So no contention, you used a CAS instruction, compare and swap, right? The unit of atomic update. Light contention, you would spin a while in hopes that somebody would let the lock go and you could get in, grab it, and carry on. But you can't spin forever because eventually that core needs to do something else. So then eventually you block and you go in the OS. Late in life, bias locking showed up for locks that were both not contended and very highly frequently executed. And bias locking lets you get rid of even a no contention CAS and lets the JIT optimize across locking boundaries. So there was some usefulness to having bias locking as well, but it wasn't where hardware transactional memory showed up. So what was the status when we started? Well, we had bias locking ahead of Sun and Oracle by a decade. We had it working and working well. Very cheap to release a bias lock. And this was part of the work done at Azul that let us stop individual threads on a reasonable set of nanoseconds. So somewhere between 100 and 1,000 nanoseconds, you could stop a thread and have it do a self-service task like count how many times it owns a bias lock and release it if it wasn't supposed to be locking it. The current implementation of bias locking at Sun, at Oracle, has to stop like the entire system, takes forever if you fail a bias lock. So not so at Azul. CAS instructions. The Azul, we know we're going to do lots of CASs. We know a lot of them are going to be junk, but they have to be there for safety. So they could hit in your L1 cache. And if they hit in your L1 cache, there were 3 clocks. Up from, at that time, Intel hardware, 300 clocks. So 100 times faster to do a CAS instruction if it wasn't contending. If it was contending, yeah, you went to main memory anyhow. Okay, what that meant was if you repeatedly locked and unlocked a lock, after the first one, it was in your L1 cache. And so you hit constantly. It was just 3 clocks, get in, get out. You still had to fence. Fencing could actually be very expensive because you might have had a lot of memory you had to go, order there. Still, it was a much better answer than Intel at the time, and about a decade later, x86, finally catches up. Light contention, we talked about. Heavy contention, I said we had, hundreds of cores. We could have thousands of runnables, hundreds of thousands of runnables. We worked well on the order of hundreds of thousands of runnables, not blocked threads, threads that are actually able to run. Fair locks in the OS, very low context switch costs. So this is sort of optimize every possible thing, and yet there's still this hole where you ended up blocking for reasons you didn't care about. Whether you spun in the spin lock or you blocked in the OS, you wanted to not be blocking, and you knew you didn't have to. The lock wasn't necessary all the time. It was mostly not necessary. So we targeted the HTM at that kind of a lock, the one that had some amount of contention, but not so much that you just must block anyhow. So what is HTM really doing here? It's letting us have a set of operations we're going to run atomically. So in parallel is what you want, but to make that work, it's atomic to all the other cores on the box. 2 or more threads running in the same code, touching mostly read-only, some set of lines, but if there's a writer, he's writing some unrelated memory addresses, and you want to make that look like all those updates happen atomically in 1 clock cycle, right? And you use the hardware to guard that transaction, and you abort if something didn't work right. Okay, so how does it get implemented? We used all of the L1 cache. So it was a smaller L1 than Intel. It was 16 kilobytes, a 4-way set associative, so you had 512 lines. But if you look at that number compared to what was available at that era, we were 1-2 orders of magnitude bigger than everybody else. It was a huge jump in size. All of your L1 was unbelievably bigger. So we thought we were way past the bounds of where it was useful. Why the L1? Because everything in the L1 is not visible to anyone else in the system. What's in my core's L1 is not visible to some other core, except when I evict a dirty line. So as long as I don't write out any dirty lines, no one knows what I've put in my L1 cache. So if I abort, instead of writing out the dirty lines, I invalidate the cache lines. And if I have some read lines that are part of the transaction, I don't have to actually evict them. I just have to clear my bits on them and carry on. So it turns out I need 1 extra bit here to mark lines as being in or out of the transaction. And when I start a transaction, the lines will all be clear, and then as I touch lines, I'll set that bit. And if I ever come to a spot where for whatever reason I have to evict a cache line, I abort instead. Okay, so in theory, the transactions are as big as 16 kilobytes. I'm going to mark touched lines with this transaction bit. As long as I don't lose the line, I'm going to be atomic, right? And so I'm just going to come in with a Java lock and say, turn on HTM, run it through, and if I don't abort, I win. That's the goal, right? And then I have fallbacks in all directions. Fast CAS if I don't need the hardware transactional memory, blocking the OS for 100,000 threads if I do, that kind of stuff. So there's fallbacks in all directions. The HTM only has to accelerate the case where I'm occasionally bumping into each other. So there's one or two more steps. I'm going to get some really sort of details here. You go after the lock, you check the lock header word, the object header, to make sure HTM is expected, maybe have to take a CAS, maybe have to inflate it. Turns out you need a lot of stats to run your heuristics to know that the HTM is working or not and when it's time to bail out and go to the OS. So you have to put stats somewhere. There's no room in the object header, so you inflate to a side structure that you hold the bits in. You decide you're going to do an HTM, you bump some counter bits saying, hey, and there's a recovery bits also in there, be jammed in. If I fail out, where the hell am I going to go to next? And then you turn on the HTM. And once you turn it on, every line you touch after that gets marked, and if you ever lose one of those lines, you lost. So you don't want to turn it on too soon. And of course, if you turn it on too late, you miss a line, then you're not safe. And then you run. You run Java code. You run JITted Java code. It would work in the interpreter, but you touch a lot more lines running it interpreted. And then you hit the unlock. It's an unlock bytecode. And if you didn't blow out by then, you committed and you were done. There was a hardware instruction for committing, and that instruction cleared the extra bits out of the L1 cache, but that was all it did. L1 cache hung on to dirty lines or whatever things you had done. It was all there. But if you would abort instead, the hardware stops, throws out, or invalidates the dirty lines that were also part of a transaction. We'll look at that in a second. And then, jumps to software cleanup. It was the hardware really just wiped out the transactional bits, wiped out the dirty lines, and jumps to a software stack, which then had to figure out which lock you were trying to hardware transact through and what to do next. You use CAS, you spin, you go to the OS, try the HTM again, whatever it's going to be. So I'm going to work through an example because it's very instructive to understand why we failed to look at an example. So we have some shared synchronized HashMap, a bunch of active readers, some active writer floating around also. Everyone wants to run concurrently, and I have some 64-bit JVM because it's a big JVM handling 100,000 threads. So you have lots and lots of heap. You got terabyte of heap, so you're using 64 bits, which means that you have not so many pointers in a cache line. Cache lines get full pretty quick. So HashMap, what's a HashMap look like? It looks like a mark word, class word, a pointer to the array, that's the hash table guts, some size bits, some mod count, some entry set cache, a load factor, some pad words. There's a lot of stuff in a HashMap. Well, then you get to the table, which is just a big Java array of pointers to entries. And there's a mark and a class and a length. And then you get entries, 0, 1, 2, 3, 4, 5, 10, 1,000, a million. You have a lot of them. And that's where you're hoping to have parallelism when a writer comes in. He's going to touch one of the million entries in the hash table, and the other entries are not touched, and so everyone runs in parallel. That's the goal. And in that hash table, it's full of entry objects, which have a mark and a class, and a key and a value and an X, because it makes it linked list. It's supposed to be short. If your hash function isn't screwed up, your linked lists are all really short. And I put everything on a cache line boundary to make my example look clean, but they're actually all misaligned and messed up, and who knows which cache lines you touch and what other cache lines are floating around. So you're going to come in with a lock. Instead, you're going to turn on HTM. You're going to load a map word, table base, table length, call key hash code, to a virtual call, do a mod to the table length, do an index into the table, load an entry, compare the entry key, maybe call key.equals, maybe read or write, maybe go to the next line, and if it all worked, you unlock. So I said a lot of stuff there. Let's look at this again. So I have a structure that looks like this. I have a couple threads coming in. The header word is marked as this is an HTM-capable lock. Let's try the HTM instead of blocking. And then I have a chip. I said, oh my gosh, what's this thing? This is my short, easy, simple version of what a piece of hardware looks like. Really, hardware is a lot more complicated. The caching layers, there are more. Intel will have 3. Every caching layer is roughly 10 times bigger and 10 times slower than the one before it. Your data is replicated. It lives in multiple places. It's in some caches and not in others. Generally always in memory unless you're writing. And then the correct value is in a cache, and the incorrect value is in memory for some time until the cache coherency protocol catches up. There is some cache coherency protocol, and that protocol dictates the correctness of these parallel independent writes. It's parallel in the land of physics. So in your real world, the actual cores are different. Things are running in parallel, not in the same spot. And the cache coherency protocol brings that together in a way that looks coherent from outside, but under the hood, it's all independently running around. And your hardware transactional memory lives or dies on that cache protocol. That makes or breaks you. So, what do we do here? I have 2 threads. They're going to try to run into this locked region and do something. They're going to test the lock header word to see if it's HTM capable or not. And I have them running in parallel, clock for clock, but that's not really what happens. They're all skewed next to each other, running a little bit more, a little behind, a little ahead of each other in reality. And in my example here, I have the caches set where the head of the map is not in the cache, so they're going to miss that piece. Some parts of the table are in the cache. So tab plus 0, that's table base plus 0, has an M for a mark. Actually, I have a laser pointer in my hand. What? M is a mark, class, the table length, and then entry number 0, and entry 1, 2, 3, 4, but they're not in this cache line because it's marked invalid. that S is for shared. These 4 values are the data in the cache. This is the cache coherency protocol, shared or invalid, and M for modified. And here's entries 5, 6, 7, and 8, and whatever else. You got 512. I can't fit it on a slide, so I had to cut it off. Along with this comes this kind of cache coherency protocol stuff. What is going on here? Well, some core asked for some cache line, and he didn't have it. And in this particular protocol, he's going to tell the other caches in the system that if they have the only version of it, a modified version, they need to write it back to somewhere where core number 1 can find it. And he only finds it in memory because this protocol is very simple and data doesn't flow on this side path, only addresses and flags saying get rid of it. So this guy is saying, CPU number 2, get rid of any copy of the map header word that you might have. And he doesn't have a copy, so that's all good. And when he's done with that, he'll go to main memory and says, give me the copy of the map header word, which has a mark and a class and a table base and a size and a pad and load factor and whatever it's gotten there. So eventually it comes to memory. Let's see here. Yeah, it goes to memory. And then they rolls back up, and you see my cache lines fill in, mark, class. So this cache line just filled in. It's shared. That's good. And the data hooks back up to the cores, and they decide that, hey, we can actually use HTM'ing here, and we should run off and begin our transaction. So I stepped through that because now you get to watch all this other stuff happen. So somebody says, I'm going to read again, where did I go here? Yeah, I'm going to read again the header word under the transaction, which puts this X bit, which says that this is part of the transactional memory. Why did I do that? Because if somebody else grabs that lock without using a transaction, I have to abort because I'm not going to be atomic if they also write outside of a transaction. So I have to touch the header word in case some other core didn't get the news that this lock is supposed to be transacted through. One of these subtle, rare race conditions. And this kind of code is full of these subtle, weird race conditions to get it going. Very, very frustrating. And the other piece, by the way, when you're debugging this shit, is that when the hardware rolls back and throws away all your updates, you can't see them in the debugger either. So it's like it never happened. And so it's really hard to diagnose what went on. So, hey, I have a key here, key 1, and a key 2 for the other core, and we're going to grab in computer hash. Now, I'm not going to show that, but to make that work, I have to get your hash code. I have to call key.hashcode. Well, that's a vtable header. I have to have the key entry in my register, but then I'm going to load a cache line with the first word of the key. Then I'm going to get the vtable out and load some word in the vtable to get to the compiled method for the hash code and some word to get the code and jump register. I load 2 or 3 more cache lines, depending, to get to the hash code to execute it, plus whatever the hash code does. So hash code probably touches a couple cache lines too. Carrying on, I go get my table base, right? We're going to go pump the table base. Here they're talking keys back and forth at each other. Hey, evict you if you've got a copy because I need the private copy. I need the shared copy, I'm sorry. Then I go get the table length. I have to wait till the table comes back. There's a little bit out of orderness, so I got a clock cycle I'm missing here. Then I got to go mod the hash and the hash, whatever your mod function is. There's a range check I'm not going to show, but I have to stall until that mod gets done. I can now do the math of the table base. I'll go to the load to entry word, and I'm getting different entry words. And so now we're telling each other caches to evict if you have a modified copy. And none of them have the modified copy because there's no modifications yet. But you can see I'm filling up with these X bits. So I'm touching more and more cache lines as I go here. And then, there we go. And now this guy has table plus 64, and this guy has table plus 32, and we send our results back to get our key. Then I have to go compare I have to load the key entry. Sorry, I got that from the table. I get the entry object. From the entry, I have to get the key. These are 2 different keys from 2 different cache lines. Again, I'm not going to show them I am going to show them in my cache here. This guy loads an entry. This guy loads an entry. Yeah, I cleverly arranged to fit in 4 cache lines, but that's not very realistic. And I evict each other if you had a copy that was modified. And all those potential evictions might blow out a transaction, but not in this case because it's doing exactly as I hope. And I test for my key being the right key, and I might have to reprobe, and I might have to call dot equals, which might be another vtable lookup with a load jump register, and then do whatever key hash code did. I generally compare those words between two objects instead of computing a hash code in one. So whatever hash code did, you touch double the cache lines when you call the equals call. And then I load some entry, or I store if I'm modifying an existing guy here. And maybe I modify, see the modified bit there? I modified an entry object on this guy, but I might have modified a table object. But I'm claiming this case is just going to work because this is my example here. It looks kind of, it's already pretty complicated and insane, and I'm just saying, hey, this one works. And now I'm done with the transaction, so I commit, which wipes out all of my little X bits. And I'm done. And you notice I didn't actually write this out of my L1 cache yet. No one knows outside of CPU2 that it did that write yet. No other piece in the system is aware that write happened. And that is part of being atomic, right? At the moment that I declare the atomicity is over, all my writes are suddenly exposed, but none have been exposed so far. So there is this clock cycle moment where suddenly I have a bunch of writes that are all exposed. You can now find them if you ask for that cache line. No one's asked for it yet, or I would have blown out the transaction. Okay, my example is just too simple. I showed 4 cache lines, 6 loads, and an extra loader store, but I need a key hash code, which I have vtable and a jump and a jump, or a load and a load and a jump. So I need 2 to 3 more cache lines to get a hash code for the key. And I have to call key equals, which has the same set of cache lines plus the computational costs of the equals. But I do that on a second key as well. So I touch a second key, the key in the table versus the key been handed. Plus, I might need to reprobe. And then I load a new entry object and a new key and repeat that process. And if I'm a writer, I'm going to touch, well, if you're a reader and writer, you touch the mod count field because you're looking for concurrent modification exception in the code. So everyone touches the mod count. And if I'm a writer, I'll check the load factor and the size to see if I need to resize. Now, for resize, I'm just going to blow out the table and give it up this transaction. Everyone will block, the resize will happen, and then we'll turn it back on and try the transaction again. So what really happens here is that to make this work, a typical successful read-only hash map is 15 to 20 lines. It's not 2 or 4. It's a bunch. And commonly, you would see 50 to 100 cache lines touched for a hash map hit, for parallel reads, because of the nature of the key equals calls and the hash code functions that we're running. Right? It was never the case. It was 15 to 20 happens, but 100 was common. You had to touch a lot of lines. So one of the lessons here is handling a small count of lines, which all the hardware up to Azul was doing some count like 4 to 8, and that was just never going to work. You had to have dozens and dozens, right? Teeny handcrafted cases or very carefully crafted Java code could get away with a dozen, but you really touched, the map, the table, the entry key, the value, plus their vtables and their second in methods and the code pointers, plus the reprobes and an extra key and an extra value, plus whatever you need to run key compare and hash code, and 2 keys in the second hash code as well. A lot, right? But then it still didn't work because the writers always touched mod count and the readers always did a false sharing on mod count. And so the writers would blow out all the readers. And it wasn't just HashMap that did this. All the container classes had some sort of profiling information floating around in them that was just thrown in to make their lives easier to understand. You have a good hash function, count your reprobe rate. Count your reprobe rate on reads. So you had a counter you bumped on reads. I'm losing my mic, by the way. I got it, okay. Which meant that a single writer aborted all readers, but that wasn't all of it yet. The lock was busy and contended, or I wasn't bothering with the hardware transactional memory. Because it was busy, I had lots of readers and a rare writer, and the rare writer would abort all the readers when he modified the mod count, but those readers would retry the transaction right away, or there'd just be a new reader because it's a hot lock. And the new reader would abort the writer because he would touch that mod count line before the writer completed his transaction. So the readers aborted the writer aborted the readers, and all of them tried again and aborted each other constantly until you gave it up and blocked in the OS. The lock failed every time as soon as any writer showed up. There was no way to get it through. And if the readers had a performance counter, they would die on themselves every time as well. So the goal here was to speed up somebody else's Java code without rewriting it. Just take your JBoss, your WebSphere, J2E app and run it. And that didn't work. We didn't get the true parallelism we needed. Turns out that it was even worse than what I mentioned here. The cores that Azul had were about 4 times slower than an x86, which meant that your lock hold times, the time you're in the critical section, was 4 times longer. But so to catch up, to play equals in x86, you needed to have a 4x count of threads running. Now, we had 100x as many cores, so the big box was worth 100 x86s. It had a lot of cores that could handle a lot of load. But when you have more threads running, the ratio of readers to writers didn't change. It could still be a 1% ratio, 99% readers, 1% writers. But the odds of having another writer in that locked region asymptotically approached 1 as you added more and more threads. You always had a writer, and the writers all killed each other and killed all the readers, and the readers killed all the writers. So 100% chance that lock failed HTM, and that was your poster child good case. That was the lock you were trying to rescue. So the applications just fail to scale. We get a big J2E web server going, we turn all the thread pools up to max, we turn all the heaps up to max, turn all the caching up to max. Giant heaps, at that era, terabyte was unheard of. You couldn't get anything close to that on x86. We 10x, 100x thread pools, everything, and add load, and pretty soon we'd be choking on locks. And you couldn't get through the locks in parallel. And that was because there was no big scale thinking in the code. People started with a small application that ran on their desktop, which was a 1 core, sometimes 2 to 4 if you were lucky. And then they went to scale. They just didn't write scalable code. They had true contention, things that were writing that you just couldn't run without doing some sort of, special lock-free algorithm, and no one had that kind of thinking in the code. So the industry as a whole was just trying to figuring out a scaling model, how to write code that would just scale and scale and scale as it added more and more load. Microservices were their infancy, and that was one of many approaches people were trying. So Azul tried, big parallel shared memory. And all around us, there's this general naivety of what would work. People just didn't know, and they were trying lots of different things. And it turns out you need a discipline to scale, some sort of distributed memory thinking to scale your code. And as soon as you have that discipline and you write your code with the intention to scale, it works for shared memory, same as it works for distributed memory. And you don't need the big shared memory box anymore. You're now going to manage, you've already thought you're going to manage your communications. And once you get that thinking in your head, you can use synchronized, but you can use software as a service or TCP sockets or microservices or whatever it's going to be. And you don't need that big shared memory machine. So we had these slow processors, and we couldn't get fast enough to catch up to an x86, except in there were some targeted use cases that it worked really well on. Outside of that, you couldn't go as fast as you needed to go. And the industry as a whole then pivoted to using clusters like Hadoop with various streaming models, like TensorFlow is a streaming models. Lots of streaming models floating around now. Hadoop's actually kind of sort of a streaming model. And it was just cheaper to organically grow your cluster. You started with your desktop, and once it got too big for that, you went to the server room and got a big server, and then you got a second server, and you figured out how to do distributed on 2, and then distributed on 4 and 8, and whatever number of distributed nodes you needed in your Hadoop cluster. And people saw problems one at a time at different levels of scale. And as the cluster got bigger and their load got bigger, they solved their scaling problems one at a time. Now, it would have been cheaper had they known up front to get a big shared memory server and do it on on an Azul box or something equivalent. But they didn't know up front which of your applications are going to scale and need to be scaled and which aren't. You mostly just code things up, and then randomly somebody comes to you and says, oh my God, everyone loves the XYZ service. We got a 2 more, we got a 4 more, we got a 10 more, we got to have 100 times bigger. And you scaled that one at a time, starting from a cheap place and adding hardware incrementally and adding programmer development cycles incrementally to get it to scale up. And eventually clusters of cheap x86s win the day. So, $250 million were spent. Mac's machine had 850 cores, roughly 100 x86s of that era, but in a consistent shared memory with actually not NUMA, but UMA, like uniform memory access times. It was really good. Lots of fun custom hardware, very aggressive HTM for that era, but it didn't work for what is intended for it to do, right? You still required you to do some major software rewriting and rethinking to get it to run in parallel, which defeated the purpose. Azul lives on, selling low-latency GCs on x86s. They have, like I said before, terabyte heaps with microsecond max pauses, and some other really cool features baked into that VM. But I quit that game a long time ago. So that's it. So we got some amount of time for Q&A.
One, yeah.
You mentioned that you have to rewrite an existing, you hadn't to rewrite existing code. And if, for example, Java had a native support for shared locking instead of just mutexes, should it have worked eventually?
If Java 8 enabled what?
Shared locking instead of just synchronized. If the shared locking was built into the language.
Well, you have a reader-writer lock.
Yes, of course, but nobody uses it. It's just simply to write just synchronized on the method, like, for example, hash table does, and just forget it.
Right. That was our goal, was to take people just use synchronized on hash table or HashMap and run through. And it didn't work for the reasons I mentioned.
Yes.
So we fixed HashMap by getting rid of mod count. And we fixed one or two other places by adding padding to get rid of false sharing. But it wasn't enough. There are too many places where people use synchronized keywords, and then they had true contention where you could read the code and understand that they didn't need that performance counter.
Yes.
But it would blow out your HTM because you had to have an atomic update of the counter no matter what you did, outside of the HTM.
But shared locking requires just one update during the transaction, just one counter, the number of readers or writers maybe. So you can.
All right. So as soon as you have an alternative locking strategy, you have to edit your code to change to use the alternative strategy.
Yes, and it was
okay.
Dated by the initial Java design.
And what I'm saying is, no one wants to rewrite their Java code. If they would use the reader-writer lock baked into the JVM, baked into JDK 5 or 6 or something, right? And you just said, no one does that. Well, that's the issue. Maybe it's time people started looking at these things more aggressively and using some of these, software locks that do at least parallel reader, from, one writer. Obviously the HTM can support multiple updates. And, these days you use concurrent HashMap or non-blocking HashMap, and you have concurrent writers as well. So for HashMap, the problem's kind of solved outside of HTM. So it's like, what is the target for an HTM now? It's got to be small enough it fits reliably in your caches despite associativity, despite whatever bad layout you have. It has to be hot enough that you care for performance. It has to be, and to get small enough, it typically has to be some tiny library code. So it's the set of spaces where it's important is shrinking to some small thing. And as soon as I have to rewrite my code around it, I'm going to rewrite it in a way that's going to work distributed as well as shared memory parallel, because it's not too much of a leap to go from shared memory parallel to distributed. And as soon as I do that, I'm on a cluster and I'm done, right? That's the game.
Thank you.
Any other questions?
Here we go, up front. Oh, in the back too. In a second.
Thank you for the talk. You broadly showed the problems with transactions when we use a large piece of common code, but did you try to implement some specific concurrently oriented structures? We just need to maybe modify a couple of pointers that can be done with single cars, and that will be favored by the HTML.
So, what I understand you asked was, did we try to reuse the HTML on our own code in different places where CAS was difficult?
Yes, yes.
Yeah, we did, and always it wasn't too hard. It was never a big win. So there were only a few places where you might want a multi-CAS, is what you're really saying. And it was usually page table updates in the kernels and context switch places that showed up. Other places, we didn't actually, we had already figured out how to run without an HTML, and the cost was low enough we never cared, right? So the JVM itself internally has all kinds of CASing operations going on for all kinds of things that you might want to have a multi-CAS HTML to work on it, except it's already been worked out using plain old CAS for all the hardware that doesn't have HTML. Hotspot's been ported to, 20 different machine architectures. So they all have CAS, none have HTML, except now there's a handful, right? So we didn't need it in Hotspot itself, although had we had it back in the day when Hotspot was being developed, we would have used it then, right? Okay. Instead, we grinded around it however difficult that was. There were some difficult things you had to do to make that work, but you could, and we did. After that, new code that used HTMLs was in the kernel a little bit, but it wasn't needed to be very much, and it wasn't a giant win. So we did it. It wasn't a big win because we didn't have that wasn't a big cost. Those things are not the big cost.
Thank you.
Yeah. And I got a question up front here too.
Could you please open the slide with actual...
With what?
With explanation of Messi protocol and...
Oh, I didn't even talk about Messi because, why?
Actually, my question is, so you're comparing hardware transaction memory with very old, like 30 years old Messi protocol.
I'm using that because I can put on a slide and talk an audience through it who's not a hardware audience. I'm well aware of other protocols.
My question is, do you have comparison of hardware transaction memory with a more recent actual use right now, modified or enhanced Messi, like MOSC with
we did
with like real protocols with use right now.
Right.
Azul this is like 30 years old, or
right.
Azul more very old, very basic protocol. Right now, there is more recent protocol of cache coherence.
So when you're done, I'll answer your question.
Yeah, sorry.
Of course, Azul used a very modern protocol, not Messi. It was a variation of Mosey with a distributed cache protocol. It was a fairly complicated thing. Showed up in Sun servers earlier because Kevin Normile, the author of the Sun multi-way machines, was also the cache coherency designer at Azul Systems. He did a great job. It was a very modern protocol. Even today, it's a common protocol used today. So that's the protocol we used, not Messi. I can talk people through Messi in an audience like this. I'm not going to try to go through a more complicated protocol because it's not the focus of the talk.
So could you please point where we can see why these contemporary protocols like MOAC or different one win the hardware transaction memory? Why they become better?
So it's not the case that the protocol is making the hardware transactional memory better or worse. It's the case that we understand where HTML works well, and there are now people targeting those cases with new code. Right? So in the case that I'm looking at here, I'm dying for true data dependencies. There's both a false sharing piece for HashMap, and there are true data dependencies for a whole lot of these containers where people are just bumping a reference counter. Doesn't matter what your hardware cache coherency protocol is, you lose to the true data dependency. I said ++, this guy said ++, I can't run it in HTML on both at the same time. It does not work, right? So it's just unrelated to the protocol, you're just dead, unless you rewrite the code. As soon as you rewrite the code, you're going to rewrite it for distributed. So that's that piece of the puzzle, right? The other thing going on in the last decade is we've kind of figured out that it doesn't work in the general case, but it does work in some very specific cases. And there's some use to be had. We didn't use it in a large, useful way, but I've been talking to people over this conference, but in others before, where they're looking at finding useful ways to use it in a much more narrowly targeted case. And there's something to be had. So I'm not saying it has no use, but it definitely didn't speed up sort of code that wasn't written with transactional memory in mind. There was no profiling tool I could hand out to my programming audience to say, hey, we'll tell you where in your code you're getting true data dependencies, and you can decide if they're important or not, and maybe change your code around so you quit getting these dependencies, and the HTML will then work, and your locks will just accelerate. So that was not a thing I could do, because I couldn't hand the right kind of profiling tool to an x86 at 2002 that some other programmer could run on their own machine and then write their code that way. So no one wrote their code with HTMs in mind, and you then failed the HTM. We got like 5 people. Boom. Okay. Yeah, once you hand it over, it's quick, but there's a bunch over there too.
This was a great talk. Thank you. So you said that when a CPU writes to a cache line, the cache line is marked as participating in the transaction, right? And
yeah,
later,
my X is showing up there.
Later abort the transaction, we invalidate the cache line.
When you abort, you throw out lines that are modified. So right here, I modified a line. That's the M. When the store happens because I'm doing a bang entry instead of a question entry, that means, hey, I own this line modified, you need to evict your shared copy, and here's the new value, and it goes into my cache as V prime, and the modified line's there. If I now abort, I'll throw this line out of my cache instead of writing it to memory, and no one will ever know I wrote it.
What if the line was dirty before we started the transaction?
You throw dirty lines out, you write them back before you mark them. And they're not part of the transaction.
Okay. So can this increase the cost?
It increases the latency for the duration of the transaction. Because it depends on how your hardware caching works here. So this goes to his question, what's the damn protocol? But see, a lot of my lines are marked like invalid here, right? And I marked it invalid so I wouldn't have to explain this very issue during the core part of the talk, right? But the invalid line, were instead to be marked with a shared line, I would simply throw the shared away and put a new line down. But where you marked a dirty line, I would have to push the dirty line out before I could fill. And that's standard hardware cache protocols. So I stall the store until the dirty line gets written out. Now, what actually happens is there's a store buffer that takes the dirty store up to some count of them before you actually stall here. And so there's another caching layer. It's the store buffer layer. It only takes stores to prevent stalling in this case. But again, I don't want to get more complicated on this slide because this is not a hardware cache CPU talk, right? This is what an HTML is and how it works. So what would actually happen there is your dirty line would hit a store buffer. The hardware would begin to evict the dirty line without modifying it, without marking it as part of the transaction. But when you go to commit, the hardware stalls the commit until he can take all store buffer writes and put them into the cache. Because he doesn't know if he's going to lose any lines until he actually fills in all the store buffer lines into the cache. You could imagine a different protocol that could work with the lines in the store buffer, same as the lines in your cache, as part of the transaction. The Azul hardware didn't do that. The Intel one is known that people don't really know how it does, but there are things that you could do here. There's a lot of wiggle room. And all these protocols, there's tons of wiggle room, a lot of choices to be made. And the choices add silicon and engineering time and rare bug cases in exchange for minor gains in performance in this kind of situation or that kind of situation. You make your choices. You pay your money, you take your chances, right? And so we did it the cheap way. You could do it a little more expensive, and it might help a little bit more. But writing out evicting dirty lines was not the cause. Evicting dirty lines that were not part of the transaction was not the reason the transactions were failing. They weren't failing because of hold time, that we held it too long. They were failing because two guys were writing the same word, and they didn't need to be.
But this means if we have a transaction in a loop that touches the same data, each time between the transaction, I need to evict this data to the memory. Right?
If you're writing continuously in a loop, you must stream data out to memory continuously. If you're overwriting the same words, the cache can hold it. So I didn't actually write. So when I committed the transaction, get rid of the X bits, right there. I don't actually write this out. If you start a new transaction and this line is modified, that's okay. If you then overwrite it into the transaction, that's okay.
Wait, but you said we need to stream the dirty line.
Okay, if you're writing new lines,
Yes.
you ran out of your L1 cache, you have to stream stuff out in order to make space for new things to go in.
No, I'm writing the same cache line.
If you're writing the same cache line, I don't have to stream it out. And when I end the transaction and clear my X bits here, I don't write that out. That stays in my L1 as a modified line. And if no one else asks for that line, it's mine. That's fine. That's the good case. I like that one. If I start a new transaction, I have to know the line has to get it's modified, it didn't get modified X. So if I start a new transaction, I still have to have the value written, known that I don't want to, oh, you're right, I have to write that one out. I will abort the line. If I write it again, I will force it. You're correct, I will force it out. I didn't think that one through. Yep, it has to be written out because I don't have any way to roll it back.
Yes.
Yeah, I'm sorry.
Add additional overheads to some groups?
No more than you would expect if you were continuously writing a line.
But if I write a line outside of the transaction,
Yeah, okay. So the deal is that the write-backs are very cheap in general because you don't wait for the result. And in the case of Azul systems, we had like enormous memory bandwidth. We never ran out of memory bandwidth. So we never stalled other than the latency to memory. So as soon as that left the L1, it went to the shared L2, where it would sit in the L2. So it was the time to write from an L1 to L2 only here. But even if it went to memory, it wouldn't stall the core. Once it shipped past the L1, the core is free to run again.
Thank you.
Yeah. Wow, yeah, I'll let you pick.
So we get it, HTML is the ultimate failure. Do you have any
I
other...
wouldn't have said it was the ultimate failure.
Do you know of any other trendy, fancy techniques we can all hype about?
Well, running 10 times as many cores that are each 1/4 the speed didn't work. So I would claim that was a bigger fail. Right? People were very much in love with the fastest possible core. Even today, right? If x86 came along, Intel came along, said, hey, I'll sell you this multi-core thing with 2 cores, or for twice the money, I'll sell you a 1-core chip that's twice as fast, straight up. What should you take? Hands down, you'd pay your money, take the faster chip. There'd be no questions here, right? Everyone wants a faster processor. They don't want more. They want one that's faster. Okay, you don't get one that's faster. You know, physics came and bit us all in the butt. So now what do you do? Well, we all become multi-core programmers, and we all learn that it sucks to be it's hard to do, and there's PhD theses everywhere, and it's an open problem, whatever, fine. Okay. Azul made the effort, and it didn't pan out. But it was a fun try. I have like 5 or 6 more minutes.
Sorry, I didn't quite get why reading and writing threads started aborting each other in cascade way, for example, in case of hash table accesses. What is overlapping there?
So, okay, so 2 things overlapped, and they were different, and I'm conflating 2 problems here at once. But let me song and dance, keep going. Oh, the clicker's going to die. Okay, here's my mod count. All the writers modify the mod count. Here's my class table base. Here's my table for the actual data structure. Everybody loads that line. Here's a cache line. This cache line gets modified 100% by all writers, and it gets read 100% by everybody. So it's called false sharing, but from the hardware's point of view, it's a true conflict. And so HashMap aborts. The writers abort all the concurrent readers. Now, once the writer aborts by modifying this line, he's given that line in his transaction. He owns it now, but a reader comes along and asks for it, and the writer has to write out his modified line before his transaction completes, so the hardware now aborts the writer. And again, this is one of these fuzzy cases where you could talk about different choices the hardware could make if it had more knowledge about which transaction to abort. In our case, we took the low-cost solution, and the last man in aborted the last one out kind of thing. And so the next guy got the line and the prior guy lost, right? So that was the continuous fail there. Now, once we got rid of the false sharing by padding the mod count to a different cache line, HashMap started working okay. You still had to have 20 lines you're going to touch, but mostly it worked. You'd have four-way associativity would blow out some of the hash maps and whatever. Some things would kill it, but you could get enough through. But all kinds of other container classes have these kinds of counters floating around in them, and that would start blowing every other thing. So if you parallel through this hash map, but you then choke on a single-threaded lock right behind it, you didn't actually run parallel very far. The time to do one hash map lookup wasn't enough extra parallelism. You had to parallelize the whole damn process to actually get some useful forward progress.
Yeah, thank you. At the end of your talk, you said that if one is ready to change actual code, it may be a good idea to change it to a distributed code. So what if we actually imagine a multi-core CPU that doesn't have shared memory at all, and programming model would be like message passing data between cores, but it seems that nobody does that. Is there a fundamental reason, or it's probably due to historical reasons?
Well, fundamental historical reasons. I go to Fry's and I go buy a bunch of cheap x86s and I stack them up in a rack, and they're distributed and they're hell cheaper than custom hardware, and they're really damn fast because Intel poured a few $1 billion into making them. So you could imagine having these chips, but you have to go beat the cost effectiveness of millions of people buying Intel hardware, so they have billions of dollars to throw on the next version of chip, so their chips are cheap and fast, right? That's your competition.
Yeah, but it may be like much more energy efficient to have like not like several thousand of units of racks.
So the cost trade-off is dollars spent on my data center versus programming man hours. Right? And that's a hard one to go beat. AMD's playing the game now. Azul systems play the game. That 1,000-core machine was the size of a dorm room fridge and drew 1/100th the power of the equivalent stack of x86s. But that wasn't cost effective because the cost of an engineer's salary would blow out your data center gains by 100x, whatever. It was like insanely bad, right? So beating the x86 monster is, everyone's fantasy, and it's really hard. They're good at what they do. So I'm not claiming you shouldn't do this, but I'm claiming you should ponder carefully your life choices before you head down this path.
Okay, thank you a lot.
Okay. Behind you.
Thank you very much. Could you please tell a few words about the current state of your business? And do you have any plans to continue your work? And the second question, is it possible to run applications written in Go language on your hardware?
Okay, so I don't work at Azul Systems anymore. I haven't worked in there in a decade. Is it possible to run Go on old Azul custom hardware? Maybe. Azul doesn't sell that hardware anymore. They sell x86s where they've tweaked the kernel to run the good GC, and they sell to people who will pay money for a good GC, right? So maybe, is that the business you're talking about? Can you run Go on the infrastructure that lets you have a low latency GC? Not without a lot of compiler infrastructure work and runtime infrastructure work on the Go infrastructure to match what you need to set up for the low latency GC, if that's the question, right? So there's a bunch of fun stuff done in the Java virtual machine that would be portable to, it had nothing to do with Java, right? It would be portable to Go, but you'd have to really go after the infrastructure in Go to make that sensible, to make that work, right? It's not like it's a plug and chug. It wasn't a open source library thing like the Takapo groups tried for years to have an open source good GC that anyone could pick up and attach some runtime like Go or Java to. And that's just a really hard thing to make go fast, go well, go work well. So you got a lot of custom work there. For what am I doing now? I've been a startup guy for quite a while. I had a startup payout a while ago. I'm kind of semi-retired. It's a nice place to be. I'm doing a couple things, all sort of unrelated. I'm doing a new programming language. It's on GitHub. It's called AA. It's a work in progress. It's a fun thing because I've always spent all my life implementing somebody else's language. So I'm implementing my own, right? Okay. It has a lot of cool stuff in it, but it's not done. You can go take a look and see where I'm headed with it and what it's doing right now. I'm working with a guy doing IoT sensors. So manufacturing process optimization. Where is my stuff inside my factory floor on a statistical probabilistic basis? It's here, it's there, it's everywhere. I give you exact timelines in three-dimensional space of all your shit moving around inside your factory with a bunch of analytics on top of it to help you discover where you have bottlenecks in your manufacturing process that you can optimize for. That's the goal. It's a work in progress. It includes a mobile app, so I'm doing React Native. I'm doing a web app, so I'm doing Elm. I'm doing MobX on React Native. I'm doing firmwares for little embedded sensors running Bluetooth. I'm doing web services. I'm doing a database in the back end to take streaming IoT data, whatever. All these parts are all in motion at once. So that's, that piece. And the last piece is remodeled and flipped my girlfriend's house, my longtime girlfriend's house. And I'm a handyman. I like doing, electrical work and plumbing and, hanging door frames and, tearing up houses and putting them back together. So lots of fun stuff, but maybe not what you're looking for. I don't know. I've stopped rocket school for a while because it was really fun, but it was also, I don't think, my best use of my time yet, but I might turn it on again someday. If there's a big push for rocket school to come back, I'll bring it back. There's some good classes there that would pay well or do well in this kind of an audience. I'm targeting people with 10 or more years of experience and or a PhD, and I have a lot of material that I can hand people. I don't know, I brought it up now because maybe it's still in the back of my head as something fun to go do. All right, I'm told I have 11 seconds and the timer has stopped with 11 seconds, so the world didn't end in 11 seconds.
But we have a little bit time.
Any more?
Questions. Does anybody have a question?
I will go outside. Oh, one more.
I have a question. So you said that this transactional memory failed, and you showed this relatively simple example of a hash map. So I wonder, did you model this, or what went wrong? Why you can?
Well, right. There was a big marketing fail about whether or not a 4x slower CPU would be worth it. The HTM itself, we built a simulator for the hardware. The simulator was running on an x86 at about 20 megahertz on the fastest possible x86 of that era. And we found any number of true race condition bugs in the hotspot VM itself. So at that time, Sun was just moving off of Sun hardware and x86 to a broader market. They're targeting Titanium, they're targeting ARM chips, targeting MIPS, whoever else was selling chips at that time. We as Azul Systems were targeting a very weak memory model hardware, and we kept finding bugs in hotspot itself. So me and Steve Goldman were racing to find who would find the next bug. He was doing Titanium, and I was doing Azul under simulation. We just didn't have time to turn on the HTM to go verify that it was going to do something useful or not. We turned on the simulator periodically to see that the simulator worked, but we didn't have time to go analyze the failure rate of the HTM under the simulation. We were just happy to get that damn simulator to run like the OS to boot, and then later, Hello World written in Java came out, and that was like spectacular. But we found 20 or 30 bugs in the JVM itself that only showed up on weak memory model hardware. I say we, me and Steve Goldman, who was an engineer I worked with at Sun, that was now not at Sun, but we were, like I said, we were handing bugs back and forth constantly there. We just didn't have time to go test the HTM under simulation. I have a fun talk on the simulator and the kinds of cool performance debugging things you can pull out of a simulator that are not obvious. I have one of the really fantastically good data race detector that runs on that simulator. The standard problem with simulator, it's 20x slower than the real hardware. But if you don't mind biting a 20x slowdown, I can give you, pretty damn good data race detection. But at these days, you can get that out of all kinds of academic papers that do like theoretical proving of it if you take a 20x slowdown. I have a totally empirical hack that works out fabulously well in practice. That's time for a different talk, though. Okay, I think I should wrap it up here. I don't know what time it is, but I suspect I'm way over bounds. I'll be outside here in one of the talking zones for a little while, and then I'm probably going to run to like the next guy's talk if it hasn't already started, because somebody's coming around after me had a cool talk, and there were a bunch of cool talks I want to go to. So catch me outside.